So this is the graphics from Wikipedia. Again, we're looking at this geometrically. So from a geometric point of view, we have a density plot and we have a curve, a two-dimensional curve. But if you look at that density plot as an actual surface, and you want to see where that curve projected on the surface goes, you can find the area under the surface along that curve. And then you can, by stretching it out, you're essentially doing a regular single integral, an integral with respect to t. And that's how t is parameterized. Yeah?
Is there a case for the path integral?
Well, this is a path integral. What? What was the question? Is there a page for the path?
Yesterday, you're distinguishing the difference.
Yeah, so this is the path integral.
Oh. What's the
Okay.
line integral?
The line integral, this is what I call the path integral, which most people also call the line integral. But then the line integral, the graphics for line integral, remember that the line integral takes in a vector field, not a surface or not a function of x and y. So let's take a look at this path integral. I'm sorry. Let's take a look at this line integral. So now the line integral is based on looking at a vector field, and then this is a two-dimensional vector field. You can call it a force field or something or whatever it is. And then you lay a path on this, a curve on this. So as you go along the curve, what you're doing is you're going and you're walking along the curve. As you're walking along a curve, you're looking at your tangent vector and you're seeing what the work being done is at each point. So at each point, you're going to compare your tangent vector and the vector that is on the vector that is on the vector field. Okay. And what you're doing is you're computing. You're adding up all those dot products, and then you're going to add up an infinite number of dot products. So that's how it becomes an integral. All right. So looking at this picture, can't pause GIFs, can you? I don't know if it's pausing. So imagine this circle as like your compass, your map. You're navigating. You're in the car. You're navigating this thing, and you're looking straight ahead. And as you go straight ahead, maybe the wind is blowing. The wind is the blue vector that's blowing around, and so if it's blowing in the same direction as you're driving, then that gives you a positive contribution for your work. If it's going the opposite direction as you're driving, it's going to contribute a negative component for your work. And then if it's blowing perpendicular to you, you know, the dot product of two perpendicular vectors is 0, so that's going to contribute 0 for your work. So that's what they're doing over here, is that they're going along this path and they're calculating all the dot products between the tangent vector and the vector field at that particular point that you're on. And then they're adding up all those contributions, and they're going to determine whether you have a positive, negative, or what the actual value is of the work that's needed. Yeah?
The little graph that you see like on the left, that's actually just after the dot product. That is what the resultant of your integrand is.
Yeah, so these are the dot products that are being added together. And there's infinitely many of them, so they essentially become an integral. Okay? So this is the line integral. The line integral takes in a vector field versus a path integral, which takes in a scalar function. All right? So let's see. Back to Jesus' question about what's this good for. And I tried to say something quickly about mass and density. So a non-geometric geometry application to the path integral is finding the mass. So suppose we use rho for density, right? So rho of x, y is some function. You want to do a function? So let's just say x times y, or x times y squared, is the density if you want to give it units, I think the units should be per area. Grams per centimeter squared or something. Is the density of a wire given by the curve C, and we could do a circle, or we could do something a little bit more interesting. Let's do a circle. X squared plus y squared is equal to 4. Then essentially what you have here is what you can compute is the mass. The mass of this wire is going to be equal to the line integral over the curve C of this density function along that curve, along the arc length of that curve. Okay? So more specifically for this problem, we have to parameterize this curve. So we'll do the standard cosine and sine. Where our limits go from 0 to 2 pi if it's the whole circle, and then we're essentially done with this problem. So we got 0 to 2 pi, and then our density function is x times y squared. So x is cosine t, let's call it 2 cosine t, and y is 2 sine t, and y is being squared. And then the dr, do you remember what the dr becomes? Square root of the derivative squared. Now we've seen circles a lot. So that's the arc length essentially. So what's the circumference of the circle? 2 pi r. Well, is that what we want? No. Let's just do it. The derivative of x is negative 2 sine t. The derivative of y is positive 2 cosine t. And so that's your dr. And then that just simplifies to 4. 2. Square root of 4. 2. Okay. And then you just carry out this integral by simple u substitution should work for this. And then etc. So then you'll find the mass of this particular wire, okay, with a path integral. So we good with this? All right. So remember that a path integral is an integral over a curve of a scalar function with respect to the arc length of the curve. Yeah?
So, what do you do for dr?
Oh, the dr the magnitude of the derivative, which is essentially the arc length, dt. Yes?
I don't, why are we parameterizing in terms of t? And why, like, when I think about this problem, what I want to do is convert ds into r d theta, and then just integrate it to theta. And then just convert everything to theta.
This is not the same as, well, first of all, polar coordinates, you're looking at two variables, and here we're really just working with one variable. And this r over here is not the same as the r for the polar variable, r.
Right. Well, that's what I mean, is that instead of just converting your drs to ds, why can't you just convert your ds into r d theta and just integrate it to theta?
Because the r is equal, r squared is equal to the square root of x squared plus y squared in polar coordinates, or r squared is equal to x squared plus y squared in polar coordinates. And this is not the polar coordinate r that we're talking about. Maybe I should just stick with the book's notation where they actually call it s. Fine. Later on, we're going to be dealing with the ds that's capital S. Is that going to be okay now? We're going to be integrating over a surface. Here we're integrating over arc length. So we're integrating over curves, and so we're using the arc length way of integrating. Later on, we're going to have a double integral where we're integrating over a surface. So that's going to use capital S. So if we want to use S here, I want to stress that this is little s right now as the arc length component. And later on, when we use capital S, that'll be capital S for surface component. We're not going to get away from confusing variables. You know, this r that I'm using is different from the r from polar coordinates. But if we change it to s, this is a little s, which is going to be different from big S later on. So you want to use s? The book uses s, so maybe. Sorry, Rob. Well, okay, we'll switch to s then. So little s. And there's also s with an arrow on top. Okay. All right, so this is a path integral. And then I tried to transition. So I think my mistake yesterday, I admit that I made a mistake in presenting this material. And my mistake is that I'm always eager to lay out all the different integrals. And so I introduced it as integrals instead of as applications. And, you know, thinking back on it, maybe I should have done an example of something where I would compute it, and then it would be an integral, and then I would do something else, and that would be a line integral that would be different. So, but from a mathematical point of view, I'm more interested in looking at the different types of integrals that we're going to come up with, and we are going to come up with another, 2 more integrals that are a little bit more complicated than this, but they're analogous to this in the sense that they're kind of giving us the same information except at a higher dimension. That's where we're going with this. All right, path integral, our transition to a line integral goes something like this. And line integral now is an integral that takes a vector field as the integrand and then dots it with a ds, the tangent vectors. Now notice how that's different from a path integral. Path integral doesn't have an arrow on top of the s, and the path integral takes a scalar function. So this is really, if you want to think about it, this is really just a multiplication, right? And then the other thing is that the ds that we saw in the path integral is actually, you need to parameterize c, so the ds is actually, let me write it like this. This is going to become more than a little sidebar here. So R will parameterize the curve C from A to B. So this symbol that we use for a path integral will change into actually a working definition that looks like this. You got A to B, and then your f function, for f you're going to put in the x of t and y of t, so everything is going to become a t. And for that I'll shorthand write it as r of t. That's saying I'm putting in x of t, y of t. And then the ds becomes the magnitude of the derivative of your parameterization dt. So this would be called the working definition of a path integral. Okay? So a line integral similarly has a working definition. And again, we're going to have to parameterize C. We can't get out of that parameterizing C. So if R of t parameterizes C, from A to B, then your line integral would look like AB. And then what you're going to do is you're going to take your vector field, which has two components. It's a vector field, right? You're still going to put in the x of t, y of t. And again, I'll use r of t for short to say wherever I see an x, I'm going to put in the x of t from the parameterization. Wherever I see a y, I'm going to put y of t in for the parameterization. But this time you're taking the dot product of x prime, y prime, which is itself a vector, also known as r prime of t. So what you get here, when you dot two things, two vectors, you're going to get a scalar. You're going to get eventually a scalar function of t, just a function of t. And then that's the thing that you're going to integrate with respect to t. If you have a special vector field. Did you hear Caesar's question? He asked, is there any way to evaluate this integral without having to do this dot product business and just dealing with the limits? And the answer is, if you have a special kind of vector field. Otherwise, you still need to parameterize this. You need to run through and see what happens all the way through, unless there's something special about the vector field. No, not quite. You still have to dot that. So that wouldn't be the case for that. All right. You have a couple of questions in your homework where they ask you if something's positive or negative just by looking at the vector field. So let's do one of those types of questions here, and then we'll do one more computation question before we move on. So here's maybe I should. I'm going to need two of these. So F is this vector field shown in this figure below. If C1 is a vertical line segment from -3, -3 to -3, comma 3, determine whether F is positive. Determine whether this line integral is positive, negative, or 0. All right. So let's draw our line, our curve segment from -3, -3, comma -3. That's down here. To -3, comma +3. That's up here. So we want to know what happens to these things. Now, you could probably just sample points and then try to get an idea of what's happening. Technically, you should look at every single point on this line, but you know that could possibly be impossible. So if I just take a point here, I would imagine that my vector field would look something like this. If I take another point that's a little bit higher, it looks like I have a vector field passing through like this. As I move along this vector field, sampling some points, I want to get some idea of how the vector field is going along there. So it looks like it's going to be vertical up here somewhere, and then it's going to go this way. So if I imagine taking dot products of these sample ones, and dot product is the magnitude of each times the cosine of the angle between them. So I'm really more curious about what's happening with the cosine of the angle between them. What can you say about all these angles that we're looking at? They're all less than 90 degrees, so the cosine is going to be all positive. So it looks like the line integral for this would all be positive. So given that information, it looks like your dot products are all less than 90 degrees, and so your dot products are all positive. So it looks like our integral, our line integral over this particular curve, let's call this curve C1, is going to be bigger than 0. Okay? All right. C2 is a counterclockwise oriented circle with a radius 3 and centered at the origin. So now let's do C2, counterclockwise, radius 3. So now at each point where my tangent vectors would be going in the counterclockwise direction like this, and my vector fields look like they're going totally opposite of that, what can you say about this line integral? Line integral is 0. C2 of this line integral is what? No, it's negative. So that's a good question. 0 would be when they're perpendicular. What does that mean? So let's do another one. Except we don't know what the curve is, so the question for you is, what kind of curves can I use? What kind of what kind of curves can I use here so that I get a line integral of 0? Any line that goes through the origin. Right? It doesn't even have to be perfectly that diagonal. It could be any line that goes through the origin, any line that goes through the origin. So if I pick this particular line right here, all these direction vectors, or these tangent vectors, the r prime of t's, are all going to be going in the same direction, and your vector fields are all going to be perpendicular. So here in this case, we have our line integral is equal to 0. Okay? All right, so is that a good visual for line integrals? All right, let's see if we can find just a problem to compute. There's a work problem here, and then a thin wire to find the mass. Let's do the work problem, because that one's going to produce a line integral for us. So here you have a field x squared comma xy, and then a particle that moves around in a circle oriented in a counterclockwise direction. So we have our standard parameterization for that. All right, let's see if we can work this out. Wait, is this the one we did last time? The field is different? Okay, let's do this. So this is going to be require a true line integral as opposed to a path integral. So our line integral, we need to parameterize C, which we already can parameterize, right? And then f dot ds. So if we parameterize C, I guess instead of using R, I'll use x and y. X is equal to 2 cosine t. Y is equal to 2 sine t. Are we talking about the whole circle? Moves once around the circle. Yeah, so 0 to 2 pi. So this is our parameterization. C colon, and then this is your parameterization. So this is our parameterization. We're going to want to find the r prime, and then we're going to want to dot it with this thing. So let's get our integral set up. Well, actually, let's take a look at f dotted with ds. And what's that going to look like? Our f function is x squared xy dotted with r prime of t. Well, x is equal to 2 cosine t and y is equal to 2 sine t. So this is my vector field with my function put in. And then my r prime is the derivative of x. That's negative 2 sine t. The derivative of y, positive 2 cosine t. And then that's it. And I'll throw the dt in there that I'm going to put in my integral. Okay? So I take the dot product. I get, let's multiply this out. 4 cosine squared t times, and then I'm going to multiply by negative 2 sine t plus, now I take my second term for the field, let's just call that 4 cosine t sine t times 2 cosine t dt. So now this is what's going to go inside of my integral. Does that simplify? Is it 0? What? It's 0, huh? So what's the integral of 0 dt from 0 to 2 pi? What?
That's 0 to 1.
0. Yeah, so this work is 0. Okay? Say it again? I think so. You got cosine squared, and I got cosine squared here. The same factor, right? 4 and 2, that's 8. And then a minus sign over here. So let's see if this actually makes sense graphically. If they ask us to use a computer algebraic system to graph the field in this circle. So I was messing around with this 3D plotter, and I was able to change the actual functions. I don't know if it'll happen now. Let's see. So our vector field is x squared, and then x times y. I don't know. What? I don't think I did, unless it did it automatically. Oh, so that's how the field looks like. And so now if we draw the graph of the curve, and the curve is a circle, right? So it's clear to me now. So they got the circle. They actually have a helix here. But what we're going to do is we're just going to let z equal to 0. And then restrict our view to 2 dimensions. And there's your circle. And you can see that if you draw tangent vectors going around that circle, that these vector field arrows are going to be perpendicular to that everywhere. That's just how it happens. That's how it graphs it. Oh, this, by the way, I was messing around with this dot too. This takes a look at flow lines. It hops on an arrow, and then it just follows the arrow wherever it goes. So in this case, it's just the vector field is either going towards the origin or going away from the origin in the radial direction. If we see a more interesting field, we'll take a look at a more interesting field. You'll get a more interesting flow line. We didn't really talk about flow lines, so. All right, I wanted to take a picture of this and put it in our notes because it kind of looks cool. And then we are all experts with line integrals now, right? Let's do another example. any path. What? What's that mean?
This is the prompt list.
No. Yeah, I know. That's what prompt says. I also talked about the line integral, how the line integral looks like. So let me see this problem with this line integral notation. Now remember that if your line integral your line integral takes on a vector field, and the vector field is a vector with components, and each of those components are functions in itself, scalar functions themselves, then we can write this vector field, or we can write this line integral as the dot product of P and Q with the parameterization of the vector field, the derivative. Oops. Right? So if we actually compute this dot product, we can see that we have P times x prime of t dt plus Q times y prime of t dt. It turns out that these are just the differentials that can be set as dx and dy. And it turns out that this is a really common way of writing line integrals. When you see your integrand looking like this with a dx plus a dy, not dx, dy together, but a dx and a dy separate, that's the same thing as a line integral. So that's what we're seeing here in this example. Okay? So I may have jumped the gun, and this might be close to impossible to do. But let's try it anyways. Let's see if we can compute this. And let's specify a specific path here from 1, 0 to 2, 1. And then we'll talk about where this problem came from and why it's stated the way it's stated. So this is a line. Let's pick this as not any path, but a line from 1, 0 to 2, 1. And so let's parameterize this path. So this is just a line segment, right? So we know that for a line segment, all we have to do is take a look at the starting point, 1, 0, and then we say t times the difference between them. So we're going in this direction, so 2, 1, minus 1, 0. So 2 minus 1 is 1, and 1 minus 0 is also 1. So our x is just 1 plus t, and our y is just t. Right? And so we're interested in dx, dy. So dx, dy is just the differentials. So dx is equal to just dt, and dy is also equal to dt. Right, so the derivative of x with respect to t, the derivative of y with respect to t with the differentials. So I got these values, and so I'm ready to write my line integral. So I have integral from, by the way, when we do this parameterization, we know that we're going to go from 0 to 1, right? So we have an integral from 0 to 1. X is 1 plus t. Y is t. So this is the first part over here. We'll call P. dx is just dt. And then next we have 2y, and y is equal to t minus 1 plus t squared e to the negative t. dy is also equal to dt. Is this easy? No. This is where I pull out Mathematica and do your calculations. I guess Wolfram Alpha would work too. What? Did somebody figure it out already? So we're going to integrate 2 times 1 plus t times e to the negative t plus t minus 1 plus t times e t squared e to the negative t. That's it. T goes from 0 to 1. All right, good. Oops. So now that we're comfortable dealing with line integrals, let's talk about this particular problem and the way the problem was stated. So remember calculus? I think in calculus there was this theorem where if you have the integral of a to b of capital F prime of x dx, that this is just equal to f of b minus f of a. What's it called? Fundamental theorem of calculus, right? So FTOC is I'd like to call it. It's the fundamental theorem of calculus, which says, this is actually just one part of the fundamental theorem of calculus, and this fundamental theorem of calculus says that if you take the integral of the derivative, it's actually just equal to the original function evaluated at the endpoints. Okay? Integral of a derivative is the original function evaluated at the endpoints. The integral of a derivative is the original function evaluated at the endpoints. So this theme of the fundamental theorem of calculus, where you're taking the integral of a derivative and it's going to be evaluated at the endpoints, will run through the rest of the semester. Okay? Starting now. Now, a line integral is the integral of a vector field, right? Now, have we studied a vector field that is a derivative of some sort? Gradient. So what if would somebody else have answered that? Okay, why don't you just pause next time if something comes out, just hold it for just about 10 seconds. Sorry. So if f if f is a gradient field, then capital F. If capital F is a gradient field, then it's a gradient of some function. Gradient, derivative, right? So let's work this out. Let's use our working definition for a line integral. So we say that our line integral looks something like this, but instead of capital F with an arrow on top, we'll just say gradient of little f. And this certainly makes sense so far. According to our working definition, we have to parameterize C. So let's parameterize C with R. So R, where t goes from A to B, for example, would be our parameterization for that. So the gradient, which is a derivative, is essentially a function of x and y. It's a vector field. It's a vector function with x's and y's in it. So I'll put the r of t in there, the x and y that can be represented by r of t. So I was doing this earlier on, right? And then your ds is r prime of t. Okay? Look innocent so far? Oh, I was going to do this earlier too. This here I blew it. I was going to do something earlier so that this would become painfully obvious. But now it's not painfully obvious, so we have to dig it out. This here, what does this thing look like? It's a scalar. The result's a scalar. I'm kind of digging now. Close, but not quite. 10 seconds, go. It looks like a chain rule. Does that look like a chain rule to you? Yeah. When do we use the chain rule? When you take the derivative of a composite function. We took the derivative of a composite function. What are we composing? F of xy r of t. Right? So this is really just a chain rule where we had taken the derivative of this function, composite function. Does that make sense? And I would invite you to look back at our notes from the chain rule. And you'll see what this is equal to. It's equal to this. Okay? So what do we have? We essentially have the integral of a derivative and what did we say the integral of a derivative is equal to? The original function, well, evaluated at the endpoints. Right? So this should equal to f of r of t evaluated at the endpoints. Let's see. F of r of b minus f of r of a. Right? What's r of b? Okay, what's r? Not quite line segment. It's the curve. The curve. What's the curve? C. Right? So this is C. And then we used R to parameterize this. And for line integrals, I think we mentioned this, but we didn't really stress it much. But for line integrals, the direction does matter, so we need a starting point and ending point. And so we parameterize this with R from A to B. So what's R of B? R of B is which endpoint? The last endpoint. Right? And then so that must mean this is R of A. So it looks like this is just a function evaluated at the starting point and the ending point. Remember Caesar's question? What did he ask? Is there a way that we don't have to parameterize? And what was my answer? This is a special field. So, can we put those together and what do we have? We have the fundamental theorem of line integrals. Oh, why don't I just copy it? I don't know. Maybe this is from a different book.
So does that mean that if you have your starting point and your ending point are the same, that you don't just zero?
Yes. If it's a gradient field. If it's a gradient field. Not all vector fields are gradient fields. Remember, somebody asked that question. Somebody asked that question yesterday. Is a vector field a gradient field or a gradient field a vector field? One is a subset of the other. So, this is the fundamental theorem of line integrals. And that problem that we did might be a good candidate for this, but we have to make sure of one thing though, right? We have to take a look at our vector field. See, this vector field is a gradient of some function. And so if we extract a vector field out of this problem here, we got a vector field of 2x e to the negative y, 2y minus x squared e to the negative y. The question is, this a gradient field? How would we know? One. Not a dot. 8, 9, 10. Okay.
You take the integral of it in terms of x and y.
Okay. Remember that if this was a gradient field, then the first component of that vector field must have come from the original function by taking the derivative with respect to x. And the second component must have come from the same function taking the derivative with respect to y. So if we anti-differentiate that with respect to x and y appropriately, respectively, then hopefully we can find f. So according to this function over here, if we take the antiderivative of this thing with respect to x and therefore treat y constant, let's take the integral of this thing with respect to x. What do we get? X squared e to the y is constant. That's it, right? And then we have to compensate for that. Oh, what if there was a constant here? But since we took the derivative with respect to x, anything with a y in it would have gone away. So maybe I have a constant, but maybe I have a function here with a y in it. Okay? So that's my first stab at my function f. Now I take a look at my second component, take the antiderivative of that with respect to y. So let's take the antiderivative of this with respect to y. What do we get? And then I would want to compensate for some constant that may have an x in it. So, does it look like we have a good candidate for f? What do you think it's equal to? It's y squared. And if you want, you can throw in a real constant now with no x's or y's. You see how this thing could possibly be that, and then this thing could just be nothing. So now we've extracted our original function, little f. Little f, by the way, is called a potential function.
Would it also work to do the doubles, fxy and fyx?
Yes. Why, yes. Sure. You guys hear what Ryan said? Let's. What did he say? Oh, he said the mixed partial derivatives, right? If this was a nice function, then the mixed partial should be equal. Let's check that for fun. Let's call this P and Q, right? So P came from the original function as a derivative with respect to x. So if I want to mix partial, I want to take the derivative of P with respect to the other variable, right? So let's take the derivative of P with respect to y. What do we get? Right? So Q came from the original function, having taken the derivative of that with respect to y. So if we take the derivative of Q with respect to x, what do we get? So actually, maybe I should keep the notation consistent here. So actually, if you do this, you can find out whether there would exist this function f, but it doesn't give it to you right there and then. It's a fast way of checking to make sure that you want to go through this process. Okay, now if we want to find the integral of this thing, we're still not done, but we can be done in a minute. This line integral over here is simply equal to this function evaluated at the endpoint minus the original function evaluated at the start point. So put 2 and 1 here. What is it? 4e to the minus 1 plus 1 squared minus, put 1 and 0, you get 1 e to the 0 power plus 0. So 4 over e. That looks familiar. Over e. Fundamental theorem of line integrals. Integral of a derivative is the original function evaluated at the endpoint. All right? So there's more terms to define here. So we might work on that later. We might jump to the next section, but we'll see. See you guys on Monday.